Most calculus asks, how fast does a number change? Differential forms ask a more geometric question. What can you add up on a line, a surface, or a volume, without depending on the coordinates you chose? Think of a one form as tiny arrows painted on space. When a curve crosses them, the one form measures signed work along the path. That is why the integral of a one form looks like this. Integral over a curve C of p dx plus q di. The symbols dx and di are not just tiny numbers. They remember direction. A two form measures oriented area. If you flip the surface over, its sign flips too. In 3 dimensions, the wedge dx wedge di acts like a tiny oriented tile in the z-plane. The wedge product is the rule for combining directions, and swapping directions changes the sign. Dx wedge di equals minus di wedge dx. The magic move is the exterior derivative. Written d, it turns forms into boundary detectors. A function becomes its gradient one form. A one form becomes a curl-like two form. A two form becomes a divergence-like three form. Then Stokes' theorem says one sentence that contains many theorems from vector calculus. The integral of d omega over a region equals the integral of omega over the boundary. Gradient theorem, Green's theorem, curl theorem, and divergence theorem are all shadows of the same idea. So differential forms are calculus with orientation built in. Local change on the inside equals accumulated effect on the edge.